Hello and welcome to our Wednesday webinar from the IEA Clean Coal Center. My name is Benedicta and I'm part of the communications team here. Our monthly webinars are based on our technical reports, which are available from our website www.iea-coal.org. Residents of member countries and employees of our sponsoring organizations can download our reports at no charge after a one-off registration. I'll just say that you can type any questions as we go along, and we'll do our best, obviously, to answer them at the end of the webinar. And today, the subject for the webinar is hydrogen production from coal, presented by Greg Kelsall. Over to you, Greg.
Okay, thank you, Benedicta. And thanks everyone for joining the webinar today. The topics I want to cover today are looking at hydrogen as a fuel, looking at the potential markets for hydrogen, looking at how hydrogen can be produced and how the costs and emissions compare for these different production techniques, looking at the strategies and supporting policies for hydrogen, and then finally wrapping up with some conclusions. So firstly, hydrogen as a fuel. It is gaseous at atmospheric pressure and temperature and is most commonly found in the form of water, but also in hydrocarbons such as methane, gasoline and coal. It is non-corrosive, although it can cause embrittlement of some metals and alloys, which has potential implications for materials choice in pipelines and system components. Gaseous hydrogen is close to being 60 times lighter than gasoline vapor and around 14 times lighter than air. This means that if released in an open environment, hydrogen will typically rise and disperse rapidly, representing a safety advantage. If released in a confined space, however, any hydrogen leakage can accumulate and reach a flammable concentration due to its very small molecular size and low viscosity. Adequate ventilation is therefore required, with the use of detection sensors recommended to mitigate the hazard, which is further exacerbated by odorants not being fully consistent with hydrogen because they are not light enough to disperse with hydrogen at the same rate. Hydrogen has a high energy content of 120 megajoules per kilogram on a mass basis, whereas on a volumetric basis, the energy content at 10.8 megajoules per meter cubed is relatively low. This is a particular challenge for storage, where to store sufficient quantities of hydrogen gas, it is typically compressed and stored at high pressures. Alternatively, hydrogen-containing compounds, which are liquid at temperatures and pressures relatively close to ambient conditions, such as ammonia and methanol, can be used as means of transporting and storing hydrogen. A useful classification for hydrogen is the colour type of classification scheme. So grey hydrogen is where the hydrogen is produced typically by steam methane reforming of natural gas or by gasification of coal. Carbon abatement is not used, so CO2 emissions for this type of hydrogen are relatively high, particularly with coal. Blue hydrogen, produced as per grey hydrogen as just described, but now including carbon abatement, typically in the form of carbon capture, utilisation and storage. And finally, green hydrogen, which is produced through the electrolysis of water using electricity generated from renewable sources. A comparison of these methods in terms of emissions and costs is presented later in the presentation. So having looked at hydrogen as a fuel, this next section will look at the current markets for hydrogen and how this might develop through to 2050. There's a growing interest in the potential of hydrogen to become a clean energy carrier in the move towards limiting global temperature rise. The primary reason for this is its ability to support the reduction of greenhouse gas emissions and to limit the point of use release of air pollutants. Analysis by the Intergovernmental Panel on Climate Change, for example, shows that pathways to limit global warming to 1.5 degrees C requires combinations of new and existing technologies and practices, including hydrogen. Hydrogen is an energy carrier rather than an energy source, which means that its potential role has some similarities with electricity. The key difference, however, between hydrogen and electricity is that hydrogen is a chemical energy carrier, which means that it can be transported and stored in ways similar to conventional fuels. It can be burned to produce high-temperature exhaust gases for power production and heating, and it can be used in largely existing transportation and utilization infrastructure, allowing the adoption of business models developed previously for conventional fuels. Looking at the current uses of hydrogen, it is supplied almost entirely from fossil fuels, with coal accounting for around 27% of the hydrogen demand, natural gas accounting for over 70% of the hydrogen demand, and electricity as an input from electrolysis accounting for less than 1% of the hydrogen demand, with fossil fuels still indirectly accounting for the majority of this, due to the electricity for electrolysis being largely produced from fossil fuels in the countries where the hydrogen is produced. In energy terms, the total annual hydrogen demand worldwide is around 330 million tonnes of oil equivalent, equating to 70 to 73 million tonnes of hydrogen per year. The hydrogen is produced in dedicated facilities, primarily local to the point of use, and its main uses are around 38 megatonnes of hydrogen per year for upgrading petroleum products in refinery applications, and around 31 megatonnes of hydrogen per year as a feedstock for ammonia production. In addition to this dedicated hydrogen demand, there is a further 45 to 48 megatonnes of hydrogen produced as byproducts from other processes, with the main users for this as being 12 megatonnes of hydrogen per year for the manufacture of methanol, 4 megatonnes of hydrogen per year in the manufacture of steel, and 26 megatonnes of hydrogen per year for other applications, such as synthesis gas for fuel or feedstock and process heating. A number of assessments of the future demand for hydrogen have been carried out. In all of these, hydrogen is seen as a necessary feature of the energy transformation. It could play an important role as part of a broader strategy, with applications which fall into two main categories. Firstly, applications where clean hydrogen is the only viable decarbonisation alternative, or where it has a proven advantage over all competing solutions. This would include current feedstocks used in the chemical industries, primarily for ammonia and methanol, feedstock for use in iron and primary steelmaking industries, and fuel for long-distance shipping. Secondly, in applications where hydrogen could become the preferred decarbonisation solution in the future. This would include fuel for long-distance, road-based haulage applications, where the main competitor would be direct electrification with batteries, using buildings to complement electrification, and storage and buffering use in interconnected power systems. The breakdown of the forecast use of hydrogen demand in 2050 is shown here, with a total demand of up to 78 exajoules, or around 650 megatonnes of hydrogen per year. So in this future, hydrogen will be used primarily for industrial feedstock and energy, together with transportation, heating, and powering buildings, together with power generation usage, including hydrogen buffering. The spread of hydrogen usage across these sectors is reasonably uniform, with significant quantities of hydrogen used in each. So looking at each of these sectors in a little more detail. Transportation represents the single largest potential market for hydrogen at around 185 megatonnes of hydrogen per year by 2050, representing nearly 30% of the total hydrogen. The primary use of this hydrogen is in transport and is expected to be in fuel cell electric vehicles, where the main competition will be battery electric vehicles, so-called BEVs. So both BEVs and fuel cell electric vehicles have no point of use emissions and thus offer the potential to significantly reduce local air pollution, especially in cities. There should be an advantage for fuel cell electric vehicles based transportation options for the large-scale segments which require long range and typically heavy loads, with the highest uptake likely to be in large cars, trucks and buses, with more than 80% of hydrogen demand for mobility likely to be in these applications. In terms of technology readiness, fuel cell electric vehicles are commercially available now or will become available in the next 5 years. There is also the need to further reduce the costs and build up refueling station networks in parallel if more automotive manufacturers are to be attracted to the fuel cell EV market. So looking specifically at the number of hydrogen refueling stations worldwide, it has more than doubled in the last 5 years, marking the path towards widespread commercial deployment. The expansion of the hydrogen refueling infrastructure has primarily been in Asia, particularly Japan and China, together with Europe, which reflects the ambition and the strong targets for these regions in the hydrogen transport areas. In North America, hydrogen refueling infrastructure has been concentrated in California and more recently in British Columbia in Canada. Outside of Asia, Europe and North America, hydrogen refueling station infrastructure and by inference, hydrogen for transport is relatively limited. In terms of industry, the industrial sector, comprising of emerging and existing feedstock applications and industrial energy use, is similar in size to the transport sector, comprising around 190 megatons of hydrogen per year by 2050. The potential breakdown of this hydrogen use is shown here, where ammonia manufacture at 44%, followed by methanol manufacture at 20%, and refinery applications at 14% are projected to be the largest users. These sectors will grow at around 1 to 4% per annum through to 2030. The methanol to olefins and methanol to aromatics demand segments are set to grow the quickest at around 4.1% per year to 2030, with nearly all of this growth coming from China. For steel, the Hydrogen Council estimates that about 10% virgin steel could be produced through the direct reduction of iron process by 2050. And if all DRI processors use hydrogen as a reducing agent, this would lead to a hydrogen demand of about 11 megatons of hydrogen per year, although a more realistic scenario could be that around half of the DRI processors will use hydrogen. For industrial process heat and space heating, hydrogen could provide 23% of high-grade heat, 8% of medium-grade heat, and 4% of low-grade heat and power, according to the Hydrogen Council. Certain high-grade heat processors require combustion-based heaters in which solids, liquids or gases are burnt as part of the manufacture process, with heat transferred to the material. Clean hydrogen can create these high temperatures while producing little or no CO2, and equipment can be retrofitted to run on hydrogen or a combination of hydrogen and other combustible fuels. For medium and low-grade heat, from typically 100 to 400 degrees C, hydrogen could complement electrification and heat pumps, potentially with hybrid boilers switching between electricity and hydrogen, which could allow factories to exploit price or supply differences. Heating and power for buildings could account for around 92 megajoules of hydrogen by 2050. Countries that are likely to lead in this market are Australia, Canada, the Netherlands, South Korea, UK and USA. These countries predominantly use gas for heating buildings and have infrastructure that can be adapted to hydrogen distribution and storage. Hydrogen has the advantage compared with electricity in that it can be stored for long periods, which is relevant as heating demand is highly seasonal. Electrification of heating using heat pumps would create a strong seasonal variation in the demand for electrical power, which would require existing additional renewable capacity to cope with this winter demand. In addition, converting to hydrogen heating may be more convenient than full electrification, as no additional space or rewiring is needed to install new equipment, and no adjustments to heating patterns need to be made. This could be an advantage for the use of hydrogen for space heating, particularly in terms of customer acceptance. In addition, gas transported through gas infrastructure provides a flexible, storable form of energy. And as current transport grids often consist of parallel pipelines, part of existing pipelines could be used for hydrogen transmission in future systems. Whether existing natural gas transmission infrastructure can be repurposed to carry 100% hydrogen depends on the type of steel and the pipeline pressure. Hydrogen by 2050 could provide around 1,500 terawatt-hours of dispatchable power produced from hydrogen, representing 75 megatons of hydrogen per year, with some 500 terawatt-hours of excess solar and wind electricity converted to hydrogen, representing 30 megatons of hydrogen per year. According to the IEA Sustainable Development Scenario, limiting global warming to 2 degrees C or below requires more than half of global power generation to be based on wind and solar power by 2050. A key challenge to achieve this will be matching supply and demand, as more power is generated from intermittent sources. Hydrogen can contribute to this transition as an enabler in renewable power storage, distribution and buffering, as well as a complementary source of clean power generation. The amount of storage required increases with a share of variable renewable energy, with several studies showing that the increase becomes significant as the penetration level exceeds around 60%. Hydrogen could therefore be a medium for storing electricity using the power-to-gas approach, although this will be predominantly a green hydrogen market, with hydrogen from electricity later converted back. Having said this, there is still the opportunity for coal to play a role, where the renewable hydrogen is reacted with CO2 to produce substitute natural gas and methanol, with coal power plant exhaust being a ready source of the CO2 needed to do this. Hydrogen can also provide clean dispatchable power, where there is insufficient renewable capacities or during times of peak demand. Hydrogen could also play a role in decarbonising current power generation. So existing natural gas power plants can be retrofitted to burn hydrogen, which could be derived from natural gas, biogas or coal. This type of application is being deployed at large scale in power projects, including the Magnum power plant in the Netherlands, Kobe power plant in Japan, which is also developing the required hydrogen supply chain from Australia, and the Keadby power plant in the UK. There is also the option to co-fire hydrogen or hydrogen storage mediums, such as ammonia, with other fuels. In March 2020, 3 Japanese companies, in partnership with Australian group Woodside, signed an agreement to participate in a feasibility study on the co-firing of ammonia in commercial thermal power plants. Turning now to the topic of producing the hydrogen to fuel these markets. Hydrogen production from coal using gasification is a well-established technology used for many decades by the chemical and fertilizer industries for the production of ammonia, particularly in China. In the gasification process, a hydrocarbon-rich feedstock, such as coal, is heated at high temperatures to produce a syngas rich in hydrogen, carbon monoxide and carbon dioxide. The syngas can then be upgraded by converting this carbon monoxide to carbon dioxide and more hydrogen using the water-gas shift reaction. The CO2 can then be separated using relatively mature physical absorption technologies such as Kelsall and Rectisol, which means that coal gasification can be a low-carbon hydrogen production technology. The process can produce a stream of hydrogen of around 99.8% purity with a final pressure swing absorption step. Globally, around 130 coal gasification plants are in operation, with more than 80% of them being China. In terms of gasification with carbon capture, there are currently 3 facilities producing hydrogen from coal, coke, and petroleum coke at scale, with a combined capacity of around 0.6 megatons of hydrogen per year, namely the Great Plains and Coffeyville plants in the USA and Sinopec Quilla in China. The Great Plains plant alone produces some 1,300 tons per day of syngas, demonstrating that large-scale production of low-emissions hydrogen using carbon capture can already be technically and commercially feasible. Additionally important to the Latrobe Valley gasification pilot plant in Australia, as part of the hydrogen energy supply chain project that will see hydrogen produced in Australia shipped to the Kobe plant in Japan for utilisation. And also interesting for the future is the Poake proposed project in New Zealand, which integrates a natural gas-fired supercritical CO2 power cycle, known as the Alum cycle, with an 8 Rivers steam methane reformer unit to produce hydrogen. So whilst this isn't a coal-based demonstration, the earlier net power Alum cycle demonstration in the US shows that coal-based operations are entirely feasible. So looking at Great Plains and Latrobe Valley in a little more detail. The largest clean hydrogen plant globally is the Great Plains Synfuel plant in North Dakota, USA, producing 1,300 tons per day of hydrogen from the gasification of lignite. The plant produces synthetic natural gas and anhydrous ammonia using 14 Lurgi Mark IV oxygen-blown gasifiers. The total cost for the design and construction of the plant was around $2 billion US, which was designed with 2 product trains to improve plant availability, so that the plant can still operate at 50% capacity if one of the product trains is out of operation. The plant began operation in 1984, using 5 to 6 megatons of coal to produce around 1.5 billion cubic meters of substitute natural gas annually. During the plant's life, it has been modified to improve productivity, efficiency, and reduce environmental impacts. In addition to the plant upgrades to improve efficiency, the plant was also diversified to produce a wide range of secondary products. Ammonia scrubbers were added to the boilers to reduce sulfur emissions and to enable the production of ammonium sulfate. And in the 1990s, an anhydrous ammonia synthesis unit was added to produce anhydrous ammonia for fertilizer manufacture. CCUS was added to the plant in 2000, capturing about 3 megatons of CO2 per year, representing around 50% of the CO2 produced at the plant when running at full capacity. And this is transported through a 205-mile or around a 330-kilometer pipeline to Saskatchewan, Canada, to be used for EOR. Second example is the hydrogen energy supply chain project, which is being developed in Victoria State, Australia, with the support of Japan. The project here aims to develop the demonstration of technologies for the production, storage, and transportation of clean hydrogen from lignite fuel in the Latrobe Valley, and to establish a supply chain through to utilization in Japan. The pilot phase encompasses a gasification plant in Latrobe Valley and a liquefaction facility at the Port of Hastings. The 500 million Australian dollar project is supported by the Japanese government and Japanese industry, together with the Australian and Victorian governments, which have each contributed 50 million Australian dollars in funding. Motivation for the project from the Australian side of the consortium is the declining domestic use of hydrogen, leaving these deposits as potentially stranded resources together with interest in low-cost generation of hydrogen. CCUS is not included in the initial pilot phase of the project due to the relatively small amount of CO produced during the pilot phase, with carbon offsets therefore purchased for the CO2 emitted in this phase. It is recognised, however, that for the subsequent commercial phase, CCUS will be needed, with the captured CO2 stored in cooperation with Carbon Net Storage Project. J-Power are leading the coal gasification and hydrogen refining facility, which started construction in November 2019 and began producing hydrogen in January 2021. The pilot phase will produce 5,000 tonnes per year of hydrogen and 18,000 tonnes per year of ammonia, which is planned to increase to 10 megatons of hydrogen by 2030. In terms of project challenges, the key technical issue would appear to be the demonstration of the supply chain to ship hydrogen to Japan, where cryogenic hydrogen transport is proposed based on KHI technology. Having focused on hydrogen production from coal, this next section of the presentation looks at how the cost emissions compare with the other forms of hydrogen production. A number of analyses have been carried out to assess the cost of hydrogen production. Notable among these are IEA, ARENA, Committee on Climate Change, Hydrogen Council, CSIRO, and US DOE. In these studies, hydrogen costs vary significantly as a function of the production technology used, together with additional factors including local factors due to geographic regional considerations, fuel prices, renewable electricity price, capacity and load factors, learning rates for both CCUS and water electrolysis systems, and the carbon tax charged for residual CO2 emissions. This means that direct comparisons are difficult to make due to the varying assumptions. However, in general, blue hydrogen production routes based on coal gasification with CCUS and natural gas SMR with CCUS are lower cost than green hydrogen based on water electrolysis, typically by a factor of around 3. This would indicate that with a large existing unabated fleet of gas and coal-based hydrogen production, the transition to large-scale, low-emissions hydrogen will require significant deployment of CCUS plants. Given the economic advantage of coal gasification and natural gas reforming with CCUS, it is likely that these will continue to be the lowest cost source of large-scale hydrogen in the near and medium term. Hydrogen produced by coal gasification with CCUS varies from $1.6 per kilogram of hydrogen to around $2.1 per kilogram of hydrogen, as shown in the US DOE reported analysis, and $2.1 per kilogram of hydrogen for coal, biomass, waste plastics-based production with CCUS. These processes are of course highly dependent on the delivered fuel stock price. Overall, the lowest cost technology appears to be that of autothermal reforming of natural gas with CCUS, with a cost of hydrogen production of around $1.5 per kilogram of hydrogen. In terms of the breakdown of the cost of hydrogen production from coal, in the case of China, capital expenditure and operating costs requirements account for around 80 to 85% of the cost, with fuel accounting for the remaining 15 to 20%. This reflects the relative complexity of the coal gasification-based approach compared with SMR and electrolysis. The addition of the CCUS system contributes to around a 5% increase in CapEx, with the largest cost addition being around 130% increase in OpEx. Analysis for the UK government by Element Energy points to there being good technology development opportunities to reduce CapEx and OpEx of gasification-based hydrogen. Based on this study, it is predicted that capital cost of coal gasification will decrease as shown in the chart here, with perhaps a 45 to 50% reduction in CapEx being possible by 2050 relative to the 2018 value, Analysis by the Committee for Climate Change shows that for a new build case in the UK, gasification plant would cost around £70 per megawatt hour, including the cost of CCUS. Future savings from economies of scale could reduce this, lowering the cost of future coal gasification with CCUS by around 10 to 15% to closer to £60 per megawatt hour by 2050. This cost assumes a 95% carbon capture rate and a carbon tax by 2050 of some £227 per tonne of CO2, such that the carbon costs account for 25% of the cost of hydrogen production by this time. The value of future carbon taxes is therefore a significant variable in the analysis of future hydrogen production costs and a potential risk to any investment decision. The potential for very high capture rates to approach 100%, as well as co-firing coal with a proportion of biomass or other waste carbon-based materials, is therefore a potential direction of development for coal-based CCUS plants. This would both reduce the carbon cost associated with the uncaptured CO2, as well as help to maintain the role of coal as a fuel in the transition to a net zero emissions future. In regions of the world which have access to relatively low-cost renewable electricity based on high wind or solar incidence, green hydrogen produced using water electrolysis could in time become a competitor with blue hydrogen from coal or natural gas. Potentially promising areas are Patagonia, New Zealand, Northern Africa, the Middle East, Mongolia, most of Australia, and parts of China and the USA. This would suggest that China and Australia in particular could be regions where water electrolysis-based hydrogen production using renewable electricity could impinge on existing hydrogen production using coal gasification. The potential cost for water electrolysis is shown in the chart here, in comparison with hydrogen from fossil fuels with CCUS. It should be noted, however, that in this analysis by ARENA, the cost of hydrogen production from fossil fuels is assumed to be constant over the period through to 2050, resulting in an increase in the levelized cost of hydrogen due to the assumed increase in carbon tax over the period. As a result, the cost of hydrogen from fossil fuels increases over time due to the assumed increase in CO2 tax cost from $50 per tonne of CO2 in 2030 through to $200 per tonne in 2050, which is not offset by any reduction through technology development or learning by doing. But as I've shown in the last slide, this is very unlikely to be the case. Focusing, however, on the water electrolysis aspect of the study, the forecast is for hydrogen from low-cost wind to start to be competitive with the upper range of fossil fuel-based hydrogen prices in less than 5 years, perhaps competing with the lowest cost fossil fuel-based technologies by around 2035. Low-cost solar PV shows a similar cost reduction profile to wind, although this would be achieved slightly later than in time than for wind. For regions where wind and solar PV resources are close to the global average, water electrolysis-based technologies may not become competitive with the upper range of fossil fuel-based technologies until after 2030 to 35. So this again suggests an important role for low-carbon fossil fuel-derived hydrogen into the medium term. Looking at the cost of electrolysis in a little more detail, as the penetration of variable renewables in electricity systems increases, surplus electricity may be available at low cost. So producing hydrogen through electrolysis and storing the hydrogen for later use could be one way to take advantage of this surplus electricity. But as shown in the chart, limiting operation to low full load hours means that the contribution of CapEx and OpEx cost elements are high, producing an overall high cost of hydrogen. As electrolyzer operating hours increase, the impact of CapEx costs on the levelized cost of hydrogen reduces, and the impact of the electricity cost element becomes increasingly important. Hence, the availability of low-cost renewable electricity is needed to ensure that electrolysers can operate at relatively high full load hours. But if surplus electricity is only available on an occasional basis, it is unlikely to be commercially viable to rely on this for hydrogen production alone. So instead, operating the electrolyser at higher full load hours and paying a higher price for the additional electricity could be preferable to using surplus electricity alone. As the operating hours of the electrolyser increase, the electricity costs also increase. And so as shown in this chart, there's an optimum level of operation of around 3,000 to 6,000 equivalent full load hours per year. This means that hydrogen production from water electrolysis should operate mid-merit at around 35 to 70% capacity factor. This may not be compatible with some applications of hydrogen, such as industrial processes where a continuous supply of hydrogen may be required. Additionally, water electrolysis needs about a half a litre of potable water per kilowatt hour of hydrogen produced, which may be a scarce resource in some areas, although desalination can be an option for coastal locations. Looking at the impact of the different hydrogen production methods, this chart shows the estimated CO2 emissions per kilogram of hydrogen produced. The carbon intensity of hydrogen from unabated coal gasification is 19 kilograms of CO2 per kilogram of hydrogen, which is around double the value of the carbon intensity from SMR of natural gas. This is, of course, an inherent feature of coal due to its high carbon to hydrogen ratio relative to natural gas, typically 0.1 to 1 for coal compared with 4 to 1 for natural gas. However, when CCUS is added, this carbon intensity can be reduced to below 3 kilograms of CO2 per kilogram of hydrogen, as shown, based on 90% CO2 capture. As noted earlier, there is the option to co-fire coal with biomass and/or waste, which can reduce the carbon intensity or move to higher capture efficiency technologies. In comparison, water electrolysis using renewable hydrogen alone is close to zero CO2, but where grid electricity is used, which contains a portion of fossil fuel-based power generation, emissions can be around 25 kilograms of CO2 per kilogram of hydrogen, i.e. higher than unabated coal. The outcome of this is that in terms of moving towards net zero emissions, the impact of water electrolysis could be detrimental unless the water electrolysis process is used at low capacity factor to use mainly renewable electricity, or until renewables penetration of a region's energy mix increases significantly, such that the carbon intensity of the grid electricity is reduced to a very low level. The approach could be for the hydrogen producer to secure green electricity mix through real-time purchase power agreements, or perhaps real-time green certificates. And the producer would then use the higher proportion of renewable-based electricity as a basis for calculating the carbon intensity of the hydrogen produced. However, analysis by DNVGL, for example, shows that in order for water electrolysis-based hydrogen production to deliver lower CO2 emissions than fossil fuels with CCUS, the carbon intensity of the energy mix would need to be lower than 75 grams of CO2 per kilowatt hour, i.e. significantly lower than the global average of close to 500 grams of CO2 per kilowatt hour. A further consideration is that electricity from wind or solar-based hydrogen production may displace the use of green electricity in the rest of the electricity system. As noted by the GCCSI, using renewable energy to replace a fossil fuel-based generation provides 3 to 8 times as much abatement benefit as can be achieved by reducing renewable energy to make green hydrogen. Their conclusion is that the most effective way of moving towards a net zero future is to produce hydrogen from natural gas or coal with CCUS, whilst using renewables predominantly for electricity generation. So looking finally at the area of hydrogen strategies and the necessary policies to support their uptake. The number of countries producing hydrogen strategies and the scale of the ambitions contained in them is increasing. Countries that have announced national hydrogen strategies or roadmaps include Australia, Austria, Belgium, the EU generally, France, Germany, Italy, Japan, Korea, the Netherlands, Norway and the UK. Looking at the first of these, Australia as an example, they published a national hydrogen strategy in November 2019, with the Australian government committing 370 million Australian dollars to advancing Australia's hydrogen industry since the release of this strategy. And Australia also published a technical roadmap for hydrogen in Australia, produced by the Commonwealth Scientific and Industrial Research Organisation. The IEA has identified 5 policy actions through to 2030, which should be pursued to increase the uptake of hydrogen in the energy transition. In general, these policy signals are needed to provide key stakeholders with certainty that there will be a future market for hydrogen. Climate policies in particular will be important, with potential actions including the establishment of high-level instruments such as emissions reduction targets or commitments to deploy certain energy resources or carbon pricing systems. A priority should be the deployment of hydrogen technologies at scale. This is to reduce the cost of fossil fuel-based hydrogen production with CCUS by learning by doing and by building confidence in the technology. So finally, wrapping up with some conclusions. The total global hydrogen demand in 2018 was around 115 megatons of hydrogen per year, which was produced local to the point of use and almost entirely from fossil fuels. This was used primarily as feedstock in the refinery and chemical industries, with coal accounting for around 27% of the hydrogen supply. The global demand for hydrogen is forecast to increase to perhaps as high as 650 megatons of hydrogen per year, representing around 14% of the expected world total demand in 2050. Hydrogen production from fossil fuels with CCUS are lower cost than green hydrogen based on water electrolysis, typically by a factor of around 3. Coal gasification with CCUS costs typically 1.6 to 2.4 US dollars per kilogram of hydrogen, with the lowest cost being that in China. Learning by doing through large-scale commercial rollout, together with cost reduction through technology innovations, could reduce the cost by perhaps 10 to 15% by 2050. In terms of emissions, the addition of CCUS at 90% capture rate can reduce the carbon intensity of this process to below 3 kilograms of CO2 per kilogram of hydrogen. Capture technologies with increased capture rates to approach 100%, including technologies such as the alum cycle based on supercritical CO2 working fluid, should be explored in the medium to longer term in the transition to 2050. And co-firing a proportion of biomass or waste materials with a coal feedstock, coupled with CCUS, could lead to net zero or even net negative CO2 per kilogram of hydrogen, which would help to future-proof the gasification plant. Near-term actions are required to overcome barriers and reduce costs to increase the uptake of hydrogen, including policy actions to send positive long-term signals to potential investors. So overall, it seems clear that to produce low-carbon hydrogen at scale, fossil fuel sources, including coal, will continue to be needed in the medium to long term, particularly for industrial uses. So thanks to everyone for listening. As Benedict has said, the draft report will be out very shortly, so I'd be very pleased if you could contact me by email with any comments on that, and I'd be happy to take any questions now. Thank you, everyone. So I'm just opening up the questions window, if you just bear with me. So the first question is, how will the use of CCUS contribute to net zero? I read that CCUS will capture only 95% of CO2 by 2050 in the UK. So as I tried to describe, current CO2 capture technologies operate at typically 90 to 95% CO2 capture. I highlighted that we should be looking at research and development into higher capture efficiency technologies, such as the alum cycle, for example, which could capture 98% or higher. And by co-firing with renewable carbon sources, so biomass and waste materials, we could move towards net zero or even net negative CO2 emissions. So hopefully that answers that one. A further question, is there a reason hydrogen derived from biomass gasification is not in your list of green hydrogen? There isn't a reason. It does also count as green hydrogen. So yes, you're right. I would include that. Although I was trying to do a comparison of electrolysis versus hydrogen from coal as the kind of main competitor to it. But yes, biomass could be a source in its own right, or it could be co-fired with coal to produce net negative or even net zero CO2 emissions. Further question, what are the challenges to achieve 100% CCUS? There are, I mean, clearly there are challenges. It's a future direction for research and development, but as I tried to indicate in my earlier answer to a question, you know, there are options to do that, but it will take, I think it will take time, and it will be part of that kind of transition for coal moving towards being a supporting role of an overall approach to achieving 1.5 degree C temperature rise or thereabouts. A further question, what will be the challenges to store the hydrogen? So there are research and development looking into different hydrogen storage technologies. I mean, currently there's the option to store hydrogen in saline aquifers, which could be a relatively low cost and easy approach. Also looking at the kind of solvent-based storage approaches where you can absorb the material, absorb hydrogen onto surfaces. So it's kind of a MOF-based approach. Hydrogen could also be stored not as a gas at high pressure, but by converting it to ammonia or methanol, which again provides a ready approach for both storing the hydrogen fuel as well as transporting it globally. Another question from Nedim Panahi. What are the funding opportunities on the topics of coal and biomass gasification? So the US DOE is running a number of funding opportunities for hydrogen, looking at both coal gasification for hydrogen as well as methane-based SME, as well as the kind of developing the technologies to be able to reduce the cost of hydrogen production. In the UK, for example, there's the current industrial decarbonisation competition, which is providing £170 million of funding for hydrogen as part of industrial clusters. So places like the Humber Zero plant, which I showed in one of the slides, is one of 6 clusters which are being funded to look at development of these technologies. So currently they're the only questions I see. So I think maybe we'll wrap it up there then. I mean, if there are more questions, they're all being recorded, and I'll endeavour to answer questions offline later and respond to everyone. So thanks again for listening in today. I hope you enjoyed the presentation. Thank you.
Thank you so much, Greg, for this great webinar. Obviously, the slides from the webinar will be available to download from the webpage of our website shortly, as always. And all that's left for me to say is the next webinar from us will be on Wednesday in May, presented by Stephanie Metzger. Thank you all for joining us today, and goodbye.